All right, welcome to our first and only challenge day of this transformation chapter. And we're going to specifically focus on translation and dilation problems with this challenge day. So first, if I have the line y equals negative 2x plus 1, and it's dilated, get this, the whole line is dilated by a scale factor of 3.5 with a center at negative 4, 1, then determine the equation of the line formed by the dilation in slope-intercept y equals mx plus b format. Now, typically, we dilated usually shapes, like maybe triangles for the most part. But if you think about it, we really dilated in those triangles, we dilated points. And so do lines have points? Yeah, lines have infinitely many points. So that's what we're really going to try to set up here in the first challenge problem. So first, let's graph our line. Let's see, where is the line y equals negative 2x plus 1? And this relates to our chapter portfolio. So we would start with our plus 1 here. So we'd start up here at our y-intercept. And then the slope is negative 2, and really, right, there's a 1 underneath the negative 2. So we could drop down 2 and then right 1. Drop down 2, right 1, drop down 2, right 1, drop down 2, right 1. And I could keep going and going and going until I kind of run off here. Or I could rise 2, but then go left 1. And so even though I go up 2 in a positive direction, when I go left 1, that's a negative direction. And still overall, negative 2 over positive 1 or positive 2 over negative 1 produces a negative slope. And so here is our line. There's our line. And again, let's put some arrow caps to indicate that this thing goes on forever and ever and ever. So again, I want to dilate this line by a scale factor of 3.5 with a center. So now let's put our center on our graph here at negative 4, 1. So since the scale factor is greater than 1, then that means we would experience an enlargement here, which means our line isn't going to get closer to the center. Our line is going to get further away from the center by a factor of 3.5. All right? So what we need are some points, right? And so do we know any points on this line that we could use? And yeah, I would go with the very, very first point that we used right here. Let's use this point, and let's call this point A. You can call it whatever you want. I'm just going to call it A. That was the point 0, 1, right? But if I'm doing a dilation that's not centered at 0, 0, then I don't really need to call it the actual real point. I need to call it by its pretend coordinate. So if I went 1, 2, 3, 4, this is really 4, 0. And if I took 4, 0 now, and I multiplied the x and the y coordinate by 3.5, then A prime is going to pretend to be at, what are we going to get? 14, 0. Now, where do I start counting from? From the center of the dilation. So there's 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're all the way right on the edge here. So there's A prime. Now, I need to do a second point because really, how many lines could I draw through A prime? I have infinitely many, right? And some of you might be thinking about what may be special about our dilated line, but we'll get to that point once we do a second point, all right? So I could use this point, I could use this point, this one, this one, this one, this one, this one, this one. Does it matter which one I do? It really doesn't matter. Some of them are going to be better than others. And I will tell you right now, and we'll talk about why after we do this, I would probably pick one of these 3 points up here. All right? So I'll just pick the next one up the road here. So I'm going to call this point B. And point B, again, we got to use pretend coordinates. So it's at 1, 2, 3, 2. So 3, 2 is where it's pretending to be. We're going to multiply the x and the y coordinates by 3.5. So 3 times 3.5 is going to give me 10.5, 2 times 3.5 is going to give me 7. So again, starting from the center of the dilation, we're going to go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and a half, and then up 1, 2, 3, 4, 5, 6, 7. So right there, there's B prime. Now, in the end, I only need 2 points to make a line. And I've got 2 points. I've got A prime, I've got B prime. So I could use my ruler, my straight edge, connect the dots here as best as I possibly can. And we can go backwards here to show that it goes this way. And now all of a sudden, maybe you start to see what's so special about our dilated line and our original pre-image line. Do these 2 lines look like special kind of lines? Like, I don't know, it doesn't really feel like they're going to run into each other ever, right? So these are, in fact, parallel lines with each other. Now, to go back earlier, why might it not be a good idea to use these points to dilate? Because if I knew that A prime was on the edge of my graph here, well, then that means that all of these points that I could have dilated, they're going to fall off the graph, and I would have to make more of a graph over here to see where they went exactly. So that's why I specifically picked points that were further up here, because I know they would be on the graph. All right. Now, we're not done, because I didn't just say graph the dilated line. I want to know what is the equation of this line. So we need a new y equals mx plus b, right? Now, a fact that we just mentioned was that the dilated line is a parallel line. So this goes back to the previous chapter's portfolio about what is true about the slopes of parallel lines. And parallel lines have equal slopes. So what was the slope of our original pre-image line? Well, the original slope was -2. So our new line also has a slope of -2. But it's going to have a different y-intercept. Now, remember, the old y-intercept for our pre-image was here at +1. Now, I can't tell exactly where the new y-intercept is for my dilated line, but if you keep going up and up and up, it is going to be something way, way up here, right? Because that's where it's going to end up hitting the y-axis. So I know that the b value is going to be something very large, bigger than 10, because I think that's the cap right here is at 10. So how do I figure out what that value was? How did we approach problems like this before? Well, we needed to know an xy point that's on this line. Do we know any points that are on this line? We know 2, right? But then here's where you gotta watch out. Because you might go, all right, let's plug in 14 into x and 0 into y, and let's solve for b. Or let's plug in 10.5 into x and 7 into y, and let's solve for b. But there's an issue with these particular coordinates. These particular coordinates are pretend coordinates, and we cannot use pretend coordinates to get the actual equation of this line. So we need to shift our attention from pretend coordinates to real coordinates. And so if I looked at A prime is really at 10, 1. B is really at what? 1, 2, 3, 4, 5, 6 and a half, comma, 8. So I could use this as my x and my y, 6 and a half and 8, or I can use 10 and 1 as my x and my y. Does it matter which one I use? No, it does not. Which one would I prefer to use? I don't know. I'd probably rather use whole numbers than run the risk of using a decimal number and ending up with still a decimal answer. So I'm just going to use the 10 and the 1 here. So this is where we temporarily, we're going to substitute in 1 and 10 into our y and our x. And then that's going to allow us to finally solve for the y-intercept for b. So then this is 1 equals -20 plus b. We're going to add the 20 over to the 1. And hey, look, we do in fact get a large number for the y-intercept. So the final answer for the equation of this dilated line is y equals same slope as our original line, but it had a new y-intercept of 21. And so remember, whenever you write the final equation of the line, y goes back as y, and x goes back in to x. We don't use the 10 and the 1 anymore. That was just kind of a temporary thing so that we could figure out that y-intercept. All right, so there's the first problem. All right, next up. Segment AB is determined by A at 7, 4 and B at 2, -3. So let's go ahead and graph these 2 points. All right, so A at 7, 4, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4. All right, there's A. And B is at 2, 1, 2, -3, 1, 2, 3. Okay, there's B. All right, and they said this is a segment, so let's make a segment. Bum, bum. There we go. All right, so if segment AB is dilated with a scale factor of 2.5 and a center at 9, 1, then what is the length of segment A prime B prime? Okay, so we're doing a dilation. We have a center given to us. Okay, so let's find where's 9, 1. 9, 1 should be right here. And we have a scale factor of 2.5. All right, so let's go ahead and do this. So instead of dilating a triangle, we just have like basically one side of a triangle, right? So we're just going to dilate A and B, but we're going to need to use some pretend coordinates because we're not centered at 0, 0. So A is pretending to be where exactly? Remember, we got to start from here at 9, 1. So A is pretending to be at -1, -2, 1, 2, 3. So -2, 3. And B is pretending to be at -1, -2, -3, -4, -5, -6, -7, -1, -2, -3, -4. -7, -4. And we're going to multiply our pretend x and y coordinates by 2.5. And we're going to multiply these by 2.5. So now pretend B prime is going to be located at what? -5, 7.5, 7.5. Oh, no, shoot. Not pretend B prime, pretend A prime. Get with it, Mr. G, come on. Now pretend B prime is going to be located at, so 2.5 times -7. Geez, oh Pete, who made up this problem? What is that, -17.5? And then -4 times 2.5 is going to give me -10. All right, so now let's graph these points. So -5, 7.5. But remember, you got to start from the center of the dilation. So 1, 2, 3, 4, 5, and then up 1, 2, 3, 4, 5, 6, 7.5. So there's A prime. And B prime, man, 17.5. Geez, come on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17.5. So I'm going to put just a little mark right here so I kind of know where I'm at. And now I need to go down 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. We're still on the graph. All right, and then I'll erase my little marker right there. Okay, and then let's make our new segment. Now, we can already tell that our new segment is quite longer than the original pre-image segment, right? And so we're going to look at this problem a couple different ways. So for right now, I'm going to go ahead and get rid of all of this. I'm done dilating. I'm done with all of this pretend stuff. I can even say, forget about the center of the dilation, because again, I've dilated my segment. I'm done with it. The only other thing I need to put down here, I forgot to put my B prime. There we go. All right, so how do I figure out the length of this segment? And some of you might be going, man, I felt like we did that, like, I don't know, back at the beginning of the year? And yeah, we did, right? We figured out what the length was between 2 points. And how did we do that? Do you remember whenever we would drop down and then go over, and we would always make this right triangle? And we used this thing called, I don't know, what was it called? The Pythagorean theorem? Do you guys remember that, Pythagorean theorem? But remember, you could have also went over and down and still made the same right triangle, but upside down. But it's still going to produce the same Pythagorean theorem setup here. So either one of those triangles work perfectly fine. So I'm just going to leave this one right here for now. Now, the way we kind of tackled this was if you have a graph, hey, we got a graph. You could count vertically and count horizontally. But I'll also tell you what we could do if we didn't have this already on a graph. All right? So let's start counting. So remember, this is a little half unit right here. So I'm going to count in the little half later. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and a half. 17 and a half. Oh, forgot that. There we go. All right. So from here to here is 17.5. Now, how far is it from down here to here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half. So all of this, 12 and a half. Now, those represented the A and the B for the Pythagorean theorem. So if I had the Pythagorean theorem, a squared plus b squared equals c squared, then we would go 12 and a half squared, 12 and a half squared, plus 17 and a half squared equals c squared. And now I need a calculator because I'm not good with halves and squaring. So let's see, 12.5 squared, 156.25. Okay, plus 17.5 squared. Let's see, 17.5 squared, 306.25. All right, equals c squared. And then I got to add those together. So I still got my 306.25 stored in there. So plus 156.25. There we go. 462.5. So 462.5 is equal to c squared. And so now if we square root both sides, if you ever have a square root of a decimal, then that is perfectly okay. Just put that into your calculator and we'll just round this. All right, so c is approximately 21 point, and I'll go 2 decimal places here, 51. Now, that is the length of segment A prime B prime. It is approximately, I guess I should put equal sign, or a approximate sign over here. It's approximately 21.51. Now, again, I said earlier, if we didn't have the graph, how would we figure out what this length was? And that's whenever we took our coordinates and we stacked them on top of each other and we subtracted. We subtracted the x coordinates and we got a number here. We subtracted the y coordinates, we got a number here. And those numbers represent the same two numbers that we would have gotten here, or that we did get there with counting. All right, so just to jog your memory on something we did earlier this year. All right, now normally I would say, all right, we're done. That's the length of A prime B prime. But I want to show you something else. Are you ready for this? We did not have to necessarily do this. We didn't have to figure out where the dilated segment was. And you might go, that sounds like crazy talk. They wanted us to dilate the segment. How could we have done this problem without dilating the segment, Mr. G? And I would say, let's talk about it. So, let me clear all this out here, and I'll leave this up here. I'll leave the original, or not the original, I'll leave A prime B prime sitting right here, and then we still got our AB. So here's what I want to take a look at right now. Let's look at the original. Here, hold on. Let me go back. This was 21.51, right? This was approximately 21.51. If we go back and look at the original segment AB, let's see how long it is. And you might go, it's not 21.51. That's true. It's not 21.51. But let's dive a little deeper here. So if I wanted to figure out how long this was, again, on my graph, I can just count, right? This is 1, 2, 3, 4, 5, 6, 7. Okay, how long is this down here? 1, 2, 3, 4, 5. All right, so if I did the Pythagorean theorem with 5 squared plus 7 squared equals c squared being just segment AB now. So I've got 25 plus 49 equals c squared, and 25 and 49 makes 74, okay, equals c squared. And if I square root that, then c is approximately, I don't know, what is that? It's like 8 point something, right? let's see, 74 square root. 8.61 if I go 2 decimal places. 8.61. All right, and so clearly this is not the same as this. But I start to wonder, how many times bigger is 21.51 compared to this 8.61? What could it be? So let's go back to our calculator, and let's go 21.51, and let's divide it by 8.61, and let's see how many times bigger 21.51 is compared to our original. It's 2.598258. That's really, really close to 2.5, is it not? So why isn't it exactly 2.5? Well, because we rounded our decimals, right? We went 2 decimal places. So what we really would find if we hadn't rounded at all is if we had taken segment AB, which was approximately 8.61, and if we multiplied it by the scale factor of 2.5, we would have ended up with the length of segment A prime B prime. So again, did we have to do this dilated segment to figure out how long it was altogether? No. So this is kind of like a new idea here, right? So if we have the length, if you know the length of a pre-image segment, and you want to figure out what the length of the dilated segment is, then all you have to do is take your pre-image length, multiply it by the scale factor, regardless of where the center is. You notice we didn't do anything with that 9,1 when we did this second version. And that will give you the length of your image segment. And that will work all of the time. All right, so now we're going to use this idea for this one, for number 3 here. So given triangle ABC, determine the perimeter and area of triangle A prime B prime C prime as a result of a dilation with scale factor 3 at center at point A. So we're going to use point A as not only point A, but it is where the center of the dilation is occurring. Okay? So again, we're going to do this 2 different ways. We're going to do it as a result of the dilation, but then we're going to also explore this as, well, what if we didn't do the dilation? Okay? And so there's going to be a new thing even that you probably wouldn't have expected beyond that, and we'll have to explore that as well. All right, so using point A as our center, we're going to need some pretend coordinates, right? So A is pretending to be the center, so A is really pretending to be 0, 0, right? So if I multiply this by a scale factor of 3, where's A prime going to end up being at? Still at 0, 0. It's not going to move. So really, A and A prime, they're at the same spot. All right, so now B. Where is B pretending to be? Again, we're starting at the center, which is technically point A. So -1, -2, -3, -4, -5, -1, -2, -3, -4. So -5, comma, -4. And we'll go ahead and multiply it by 3. So B prime is going to pretend to be at -15, comma, -12. And again, we got to start from A, the center of the dilation. So 1, 2, so we already know this is 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then down 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whew. All right, there's B prime. All right. Is that right? Did I count that right? I feel like I need to start over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, yeah, I did that right. All right. C is going to be at 0, comma, -1, -2, -3, -4, -5. So 0, -5. We multiply that by 3. And C prime is going to pretend to be at 0, comma, -15. So moving over 0, but down 15, I already know C is down 5, so 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Here's C prime. All right, so now I need to make my new triangle. So A prime, B prime, B prime, C prime, C prime, all the way back to A prime. So what I've been asked to do is determine the perimeter and the area of this new triangle A prime, B prime, C prime. All right? So for right now, I'm going to pretend like I don't know really any of this. Well, let's see. How about we hold on to our prime coordinates. So at this point, we're not really pretending, but we could still use these pretend coordinates because they're all based off the same center point here. So let's see, can I move this down? Cool. Can I move this up? Oh, of course, it's attached. You're attached. All right, so you know what? Let's just forget about all this for right now. Okay. So perimeter, I have to figure out what the length of all three of these sides are. And are any of these three sides easy to determine? And I would say, yeah, one of those sides, this side, right? It's perfectly vertical. I can count that. And how long was this perfectly vertically down? Remember, we went down 15 from A to get to C prime. So this length, I'm going to start using a different color now. This length from here to here has a length of 15. Okay. Now, how do I figure out the length between A prime and B prime? Didn't we just do something like that? I don't know. Back in the last example? We did. How did we do it? We used Pythagorean theorem, right? So let's think about this right triangle that's right here. And again, we got the graph right here. We can do the counting. We can go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, all right, so here's 12. And then this is, let's see, 1, 2. No, wait, how far did we go over to get to B? We went over 15, right? Yeah, we went over 15. So this should be 15. I hope I'm right, because otherwise it's going to be a terrible mistake. But I'm fairly certain we went over 15. Okay, so 12 squared plus 15 squared equals C squared. 144 plus 225 equals C squared. Those add up to be a 9 and a 6 and a 3. And we're going to take the square root of that. Now, here is where I'm not just going to plug this into the calculator. I am actually legitimately, like we have done previously this year in a chapter portfolio, I am going to simplify this square root. So I need to try to find some numbers that go into 369, preferably something like a perfect square. Now, I definitely know that 3 is going to go into this, but maybe let's check 9. Let's see, 369 divided by 9 is 41. Sweet. So here's a good starting point here. So I can break 369 into the square root of 9 times the square root of 41. And the square root of 9 is a perfect square, which tells me 3. 41 is prime. It's not going to break down anymore. So the length of this side over here is 3 times the square root of 41. Exactly. No approximation there. All right, so there's two sides down. We've got 3 root 41. We've got a 15. Now we just need to come down here and figure out the length of side B prime. That's not the color I wanted. B prime, C prime. How are we going to figure out the length of that? Well, we've got a much skinnier right triangle to do the Pythagorean theorem with. So let's see. 1, 2, 3. And then from here all the way to there is still going to be 15. All right, so now I'm going to erase this. So hopefully you had all that written down. We've got 3 squared plus 15 squared equals C squared. We got 9. We got 225. All right, that's going to add up to be, what, 234. All right, square root both sides. And again, I need to try to legitimately simplify the square root of 234. So 234, even number. I don't know, maybe let's start with 4 as the smallest perfect square. And that doesn't work. So I could try some bigger stuff, but I'm just going to start breaking it down to some 2's. So I know 2 and 117 So I'm going to try the repeated factor method here. And then can I break down 117? Yeah, 3 can go into 117. How many times? 39. All right, so then this is still a square root of 2, but now this is a 3 and a 39. And so I still keep a 2, I still keep the 3, but 39 can break down into a 3 times 13. So again, this is a 3, but it looks like a weird number, so let me just rewrite it. And then all of these are prime numbers at this point. All right, so we've got a pair of root 3's. That's going to turn into a square root of 9, which turns into a 3. And then I have a couple leftover square roots, a root 2 and a root 13, which means I just multiply them back together into a singular square root. So 2 times 13 is 26. So in the end, the length of segment B prime C prime is 3 root 26 exactly. Okay, so now let's answer the perimeter question, which is actually going to be the tougher of the two, perimeter versus area. The perimeter, and then I'm going to make this like subscript, kind of like what we do with translations and dilations with the scale factor, and really rotations and reflections. I don't know why I specified translations, but capital P perimeter, triangle A prime B prime C prime equals, and now I need to add up all 3 of my sides. But here's the thing, none of these sides are really like terms with each other. So the perimeter is just going to look like this, and it's going to look a little weird, but it's going to be 3 times the square root of 41 plus 3 times the square root of 26 plus 15. Now, if I want, I could figure out what that is approximately as a decimal, and you could do that if you want, but this is the exact answer, and this is the way that I'm going to leave it for right now. All right, so there's perimeter. Now we got to do area. Oh my gosh. How have we found area of triangles so far? And the main thing we've done is 1/2 base times height, right? And remember, one of our 3 sides has to be the base, and the height had to be perpendicular. It had to make a 90-degree angle to the base. And so do we have any sides of our triangle that would be a really good candidate for the base? And if some of you are going, yeah, how about this guy right here? Because where would the height be at? Well, the height would start at B prime, and it would have to drop perpendicular, and we would make this natural 90-degree angle, right? And this is a horizontal piece. How far is it from here to here? Well, that height would be 15. So the base is 15, the height is 15, so the area, 1/2 base times height. And some of you are going like, man, Mr. G, it's been a while since we've done area and perimeter and Pythagorean theorem. Hey, guess what? This is honors geometry. We're going to be doing some old stuff off and on all year long, so buckle up. Here we go. So the area of this, half of 225 is 112.5, or 112.5. So there is the area of triangle A prime, B prime, C prime. All right, so there's really the answer I'm looking for, right? But guess what? There's a twist. Could we have done this problem without the dilation, without actually seeing triangle A prime, B prime, C prime? Could we have just used the original triangle, ABC? And could we have just used the scale factor to also get these 2 answers? And my answer to that question is yes, and yes-ish. All right? So I'm going to kind of pause because I believe I'm going to split this video up into 2 parts here. So I'm going to call it a day with this, and then we're going to explore this concept in the next video.